Hello and welcome to the second part of hexagonal multi-surface pattern in Grasshopper. In this session, we will continue from where we left off in the first part. We constructed a planar orthogonal grid of points that serves as the foundation of our script. And the script, let me remind you, is meant to generate a seamless hexagonal pattern across multiple surfaces. Today, we will enhance our grid and add new features and move the project forward. But before we do that, I owe you an explanation of how to bring nodes onto the canvas more effectively. In the first part, I used the main palette and manually search for each node. This is not the intended workflow. So let's cover the proper way of placing components first and then return to improving our grid. Okay, so there are two methods of bringing node. So the first one you already know from the first lesson. You go to the palette, you manually pick the node, you place the node onto the canvas one by one. Alternatively to that, you're going to use another method which basically give you opportunity to search the node by its name or a nickname. So if I will double click, you're going to see that I will have this input field, and it says enter a search keyword. You need to type the name of the node. For example, we already know a couple nodes. For example, this node called series. So if I will type series, here it is. I will have an option to quickly call the node series. Let's try something else. Let's say panel, right? So double click, type panel, and here we have ourselves a panel, right? Now this is cool and all. It to some extent speed up the workflow, but not significantly, because some of the nodes can be has a pretty long name. For example, this node called construct point. So if I will try to do it, I need to manually type construct point. Yeah, here it is, right? And if you made a typo, it will not find it, so you need to delete what you wrote and then start over. That's not very convenient. And because of that, Grasshopper has this kind of search field, and the search algorithm has additional layer of complexity through the nicknames. So basically, it called a quick callout, and I'm gonna use a specific nickname for my nodes to call them quickly. For example, and some of them already in the Grasshopper. For example, by default, if I will type quote mark, it will immediately call me a panel. Here it is. Let me try again. So I don't need to type panel again. I type a quote mark once again. Here we go. Same with the sliders. If I will just bring number like 20, it immediately considers that this is probably a slider I want. And yes, please. So here it is, 0.1, another slider. Now this is called a quick callout. What's good about all the system is you can construct your own. And unfortunately, Grasshopper, the first version, the Grasshopper 1, which we see right now, doesn't have hotkeys for the nodes, like in the classical way, like a hotkey doesn't have it, but it has a quick callouts. In the Grasshopper 2, by the way, which is still WIP, still work in progress, and probably will be for upcoming, I don't know, 2, 3, 4 years, it actually has hotkeys already in the system. So how are we going to bring this concept? How are we going to add our quick callouts? Well, actually, very simply. First of all, let's bring the construct point node here. So I'll type construct point, this one. All right. And while my node is selected, I will go to File, Create User Object. And here I'm going to see I have a new menu with two very important fields, the name and the nickname. You're going to change one and another one, but something shorter. Like, for example, instead of a name construct point, you can type CPO, for example, and leave the nickname as is. Or you will leave the name construct point, so there will be no confusion, but you change the nickname. I will do the second thing. I will change the nickname. So I will type CPO, for example, like this. Now, this is another field called category, and for me it is test by default. For you, probably something else. You can change that. This is a name for a tab in your main palette. So when I'm happy with my nickname, I'm gonna click OK, And you're going to see that in my main palette, a new tab appears called test for me. So if I'll open it up, you're going to see that now I have this construct point node. It is a duplicate of original, a duplicate. It's called the same, it has the same name, but it has a different nickname. So right now, if I will double click and I will type CPO, here we go, construct point. Let me show you again, CPO, construct point. And that's how you're gonna use custom callouts for whatever node you want. I will not tell you which one. I won't suggest you which one you want to add as a quick callout. It's obviously up to you and your personal experience. But in general, the nodes you use more often, you basically go in and go through this kind of pretty simple steps and construct yourself a quick callout for them. And of course, I have a couple of my own. So, for example. And oh yeah, before I show you the example, if you right now close the session, you close the Grasshopper, you close the Rhino, you open it again, this duplicate with your custom quick callout will persist. All right, so this is a persistent change. If I will delete it here, right click and delete user object, and as you can see, it was the only one in the group, so the group is now is no more, and this will be a persistent change as well. So if I'll open up again, I will not have it anymore. Right, so here's a couple examples for you. So for example, construct point for me it is CP, deconstruct point, DP, construct path, CPA, deconstruct path, DPA, like, I don't know, list item, LI, and so on and so forth. So I'm not saying that you're supposed to change all the nodes with all the custom quick callouts, but just the ones you really oftenly use. You probably don't know which you oftenly use because you just started your journey, but with time, you will just add this to your list and you add your own custom quick callouts. All right, so these are out of the way. Now let's get back to our test. Let me turn on the node again. Once again, this is Control Q. And look at what we did before. Now, in the previous session, we constructed this grid as a foundation of our script. It's very minimal and very simple, and we're able to construct it because we know right now basic concepts of data management, data merging, data grafting, data matching. This is all nice and good, but this grid in its current form lacks controls and lacks options. So what I want to add to this, first, I want that my grid will have an option to rotate. So I'm going to specify the angle and it will rotate around the center on, well, angle I decided, like for example, from 0 to 90 degrees or from 0 to 360 degrees, which means full period. And of course, we don't have it right now. On top of that, I can't, using this grid, bring additional rows and columns as a separate entity. Like for example, like I need another column, right? Well, I can't do it right now. So I need another column or another row, if you can call it this way, on X, or independently another row in Y. I don't have this capability, so this is something I want to add as well. And last but not least, the values are not normalized, meaning that if I will bring my series here, you're going to see that the values, they are defined by the step. So 0, 20, 40, 60, it's a pretty big numbers, right? So the grid is not really that small. But what I want to do is that I want that whatever amount of divisions I have or amount of points I have, I want that all of the values or that construct these points, X component to Y component, by default, the original grid will be shrunk to the unit domain, meaning from 0 to 1. This is the concept of normalization. Now, this is really important for us. It's difficult to understand why just from the get-go, because it's foreshadowing things. But let me tell you that we're doing it because eventually we need to work with surfaces, and surfaces, of course, has their own domains. They can be normalized or not normalized. They can maintain aspect ratio or not, and we need to think about that beforehand. So if I will not introduce this ability right now, it will be a pain in the ass later. So this is a must, and later when we bring surfaces, you truly understand why we actually normalize that and truly feel the reason of that. Okay, so let's do this one by one. And first of all, actually, you know what, I will just leave it be here, and I will just start over. There's only 3 nodes, so not a big deal, right? So let me bring a couple of variables here, right? So double click and I will type the number, let's say 5, okay? All right, this is my number slider. Now this one, I want to change the name. To do that, I will right click and select the field, then I will type, well, what will it be? It will be a division. Let's say it will be division on X, so we'll type div X, all right, like this. Okay, now I will select this, Ctrl+C, Ctrl+V, and this one will be a division, let's say Y. All right, so now instead of a one slider, I have two independent ones, which defines the amount of steps. And then, as I said, I need additional controls for additional components on X direction and additional components on Y direction to construct additional rows and columns independently. So select this, Ctrl+C, Ctrl+V, put it down. Let's say that this one will be right click, let's say, I don't know, let's say type it just +X, and this one will be +Y. Okay, and let me just set them to 0 for now. Right, now let's talk a little bit about the selection, because as in many more modern tools, the Grasshopper has two different ways of selecting things or different consequences or results. So if you select, you use this kind of selection rectangle from left to right, then to select any node, you need to fully cover that like this. All right. So if you're not doing that, it will not select it. Alternatively, from right to left, you're gonna just pick it just a little bit, and it will be selected, right? So just FYI. Now I will select all of them, and here I have a little bit of additional controls to organize my my nodes. I will click on this button to align them to the left, so they will be a little bit more organized. Right, now as I have division X and division Y, you're going to see this is the number 5. But I said just a minute ago that I need that my numbers will be normalized. I don't want to change these numbers, but I like themselves as type like 0.1. No, so these numbers stays where they are. It basically defines how many divisions I want. But the actual output is supposed to be shrunk into the unit domain, or to the domain between 0 and 1. And I'm gonna do it using the normalizing operation. Basically, I will normalize the domain, and I will do it through the concept of division, because there are different ways of normalizing values, and there are different ways of normalizing domains. We will be looking through the concept of normalization through division. It suits us really well. It's very easy, so we go for this first. But to understand the concept of normalization, we need to remind ourselves what is division. You probably say, well, Alex, we know what the division is, right? Like, for example, let's say 10 divided by 2 will equal 5, right? You're probably asking who you think we are, right? It's a child play. We know what the division is, because the division is a slicing operation, right? Well, that's what you taught in school. I don't know what kind of a degree you have, what college you finished, so I don't know your actual understanding of mathematics. And in school, that was legit. Yeah, this is a slicing operation. You slice 10 by 2, and it will get by 2 parts, and the every part is with the size of 5. All right, but these slicing operation concepts, once again, it's oversimplified because its division is not slicing operation. Here's another example. For example, let's say 1 divided by 0.1. What the result will be? Well, the result will be 10. Well, why 10? What does it mean 0.1? How are we gonna? Here we, slice it by half, and now we are slicing it by 0.1. Like, what? Like, it's not really a very convenient explanation right now, isn't it? And that's because it's not a slicing operation. Division is an operation of comparison of scales. So we're going to think about this way. How many times 2 fit into 10? It fit 5 times. How many times 0.1 fit into the 1? 10 times. From this perspective, everything becomes to be very logical. Yes, of course. That's actually what is division. Division is a comparison of scales. When you have the scale of a dividend and the scale of a divisor, right? And this number, I believe, is called quotient in English, and this is actually our factor, right? Okay, so how it all helps us in terms of the normalization? Well, very simply, the normalization is a very specific dividend and a specific divisor. So by normalizing, we shrunk whatever number, we shrunk the number which is bigger than dividend into its representation in this domain. So basically it looks like this. The actual formula is 1 divided by x, or x with the power of -1. And you know what, indeed, if you, let me just kind of, I don't know, I believe I have it in my calculator, right? Because every calculator has this. Yeah, so here I have a calculator. You can see this 1 divided by x. Well, this is the normalization. This is exactly what it is. So if you ever wondered what this does, what it does, normalization. So what happens here is we have a number x, so x supposed to be bigger than 1, so bigger than the actual unit domain here. All right, and if it is bigger than it, we're gonna find how many times it fit into the 1, and it will be basically the shrunking operation, right, or different representation for the scale. We're comparing scales. Let me visualize it now using nodes. How we're gonna do it in Grasshopper? Well, we're gonna use a node called expression. Now the node expression locates under the math, under the script, this one expression. Now, of course, let me call it expression. Oh, and by the way, I forgot, do I mention it or not? Because just really didn't really realize, but you can double click to open up the search field, and of course you can hit a spacebar as well. Spacebar does the same thing, but it always centered, just in case. So here we have our field, and it basically our expression field. It's what it is. So I can use expressions here, plug my variables. I'm going to zoom in. I'm going to say I bring more or less, and basically it solves the variable for me using existing expression using existing variable. So let's type our formula. Remember, 1 divided by x. Okay, our concept of normalization. So let me just kind of leave only 1 for now. So I will put 5 into 1 divided by x, and in the result I will use panel to analyze. You're gonna see we effectively represented the number 5 in the domain of 1, right, for 0.2, and you're gonna see that the number can increase or decrease, right? Very nice. So that means that whenever number we have, it will be shrunk once again from 0 to 1. Now we need to modify this a little bit. So right click and drag to disconnect. I will zoom in, click again, and I will use this node. I will right click and change that variable. Let's say this one will be x1. Okay. Actually no, let's do it a little bit later. Let's focus on these one first, and I will plug 1, and I will hold shift click and plug another one. So basically I'm using 2 data trees. You probably remember our description of a data matching, right? And I basically use both of them and push it through the same formula, and it will give me the same result where we have 2 numbers, because there is the one number which goes from 1 divided by x, and then the number which goes from 1 divided by x, and I will get 1 data tree with 1 branch and 2 items, because you already know, because this branch, this data tree and this data tree has the same branch number, so they merged together through the concept of merging. Okay, so now they have 2 values. What we're gonna do next, we'll bring our series node once again using the search bar. So I'll type series, and that will be my step as well as in the original example. So I'll put it into the step. So I have steps, I have 2 steps, 0.2 and 0.2. One will be for x, another one will be for y. Right now they are identical, but they can be different, right? Let's say that they are identical for now. Now let's talk about the additions. So this is additional number or additional division, which I can add to my original set. How I do it? Through the expression field as well. So let's type expression again, and here I will type let's type x plus let's say x1. Okay, so I will put division x, oh my god, division x, oh, that's just a right click, let's type x1, and then the additional x, and I will get 5 plus 0. It gives me the number 5, right? Now, before we move on, very, very important thing is that this is the amount of divisions, right? So if I look at my series, like if I'll plug it here, if I look at the series, I will get the series of numbers using this step and this count, which is 5. How many numbers do I have here? From 0 to 4, I have 5 numbers. But remember, this is amount of divisions. How many divisions do I have? Well, this is basically the gaps between them. 0, 1, 2, 3, 4 in total. But I said 5 plus 0. I said that I need 5 divisions. Not the actual amount, not the count, but the divisions. What do I mean? What do I need to do? I need to add 1. So I'll go in x plus x1 plus 1. Like this. Right now I have 5 divisions. I said that I will need to 5, and I have 0, 1, 2, 3, 4, 5 in total. Well, that's correct. Now, if you're confused, once again, we are decided that we want to have divisions. This series doesn't give us divisions, it gives us the series of numbers. And the series of numbers will be always on one more than amount of divisions, right? Because we have a series of numbers and you just calculate the spacing between them. That's our divisions, right? So I believe that's quite obvious why we need another one here. All right, so this is our x. What's about the y? Well, we can do the same with the y. Control-C, Control-V. This is my y and y. Here it is. And now you already know how we're going to merge two elements together, because this one, as you can see, we have the data structure, the data tree with one branch and 2 items. This one is a step for x, this is the step for y. And we have 2 sets of values. One is the divisions for x, and another one is divisions for y, right? And the current amount here, by the way, let me just kind of just make it a little bit more convenient here. y1, because this is y, right? So I want to eliminate some confusion with the variables for now. Okay, so and now what we're going to do is we need to merge them together. So we will have the same data structure, 2 elements here and the 2 elements there. And you already know how to do it. We're using basically 2 of them together like this, or merge operation. So merge, a more effective one and another one, and we'll have ourselves 2 values. So we're not going to plug that into the count. All right. All right, cool. So now we have ourselves a set of numbers, and we're actually going to go in. I will just duplicate the original construct point, and I'll plug that in just to visualize what we have briefly, right? So if I'll zoom in, you see how small the grid is, because all the values goes from 0 to 1. All the values go from 0 to 1. And if I will increase the amount of divisions on one side or another side, right, you're going to see that this is not actually the proper way of doing stuff. We need to tweak it a little bit. Actually, let me just kind of tweak it first, because it probably will be a little bit confusing. So then we go back to our normalization operation like this. So before we actually construct the proper points so that it will be unbreakable, we need to separate this on 2 parts, right? So now we have one data tree with 2 tree branches. One of them is components for the x, and another one is components for the y. And of course, I can increase one or decrease another one, and you're going to see that we have a bigger list compared to the smaller list, right? And of course, that's where you're probably remembering what we did here. We used the data matching operation, right? So we used the data matching operation based on the node called longest list, this one, right? So we grafted this one of the lists, and that gives us an ability to construct the perfect pairs. And if I'll just plug this one directly, it will work if I'll have the same amount of x and y. But of course, I can have a different ones, and I probably need, get a little bit ahead of myself. So I kind of need to bring these this data for the data matching, either from the separate data matching structure node, or through the construct point node. Because if you remember, construct point node has data matching built in. But remember what we did before. We used two separate lists. Here we have a one big list. And if I will take this list and graph that and put it like this, with the repeat last, what do you think will happen? Well, bad things will happen, because now if we calculate, you're going to see that we have a complete anarchy with our structure, and you're going to see that some of the stuff just repeats itself over and over and over where it shouldn't. Why? Because they are a one data tree. And the fact that this branch has more elements and this one has less elements will not change if I will graft one of the inputs, because I'm grafting both of them at the same time. So what I need to do, I need to separate this data on two different data trees. So instead of a one data tree with two branches, I need one separate data tree with one branch, this one, and another one with this one. How are we going to do it? Well, for that, I will need to introduce you to the additional node for the data management node, which is called explode tree. It locates under the sets tree, explode tree, this one. So we already know the concept of merging, right? So we merge data together, we can graft it, and so on and so forth. Well, this is the operation which separates the branches, right? So if I have more than one branch, it will separate it on individual data trees. And if I'll plug the series here, you're going to see that I have one branch, the first one, which is our X, and another one, which is our Y. Very convenient, right? And remember, right now we have 8 divisions in X and 5 divisions in Y, so we have the different amount of elements, right? And now if I'll plug these elements, let me just kind of do it this way. So I will use these ones as my X and this one as my Y, and I can just directly right now plug that into my construct point node. I don't want to go through the data matching again. I believe you understand the concept of longest list already. Now, as you can see, we have the proper data structure, and it's not breaking itself anymore, right? No problems. All right, so it's temporary. We need some more additional operations here, but we did it a little bit prematurely, so I will show you the concept of normalization. So once again, if you look at the numbers here, you're going to see that it goes from 0 to 1 and from 0 to 1. If I will increase one of them, right, the data structure is correct, the grid is correct, but you're going to see that no matter what we do with our base inputs, it will be impossible to get a value bigger than 1. They always shrunk into 1 because of the concept of normalization. But these additional ones, plus X and plus Y, doesn't go through the concept of normalization. They have the same step, and the step is our current value, like 0.1111 or 0.2. And if I will increase the step will use the same correspondent, I increase the amount of rows, it will inherit its own step, right, from the current values 9 and 5. Right, and this is how we're going to add or remove additional parameters, right? And what's important here is that if I look at the numbers, here, let's the series, you're going to see that now we're going beyond the 1. But that's okay. As I said, we need to have a core fit into the 0 to 1. Everything extra can and should go outside of the boundaries, but with the same step, right? And that's exactly what we have. Once again, you will understand in full detail why we really need to do that when it comes to the surfaces. We are not really have any surfaces here, so it's probably looks like unnecessary step, but trust me, it's very, very important. All right, so what we already did, we already normalized our grid. We brought a possibility to independently change the amount of divisions for X and for Y, as well as we give an independent, the ability that can independently grow or shrink the rows and columns for X and Y individually. Right, before we move on, let's look at this structure, because this, even though that I believe it's really, really obvious what we did, it's a little bit like it's just to have like a 3 nodes actually for these operation x plus x1 plus 1 is a little bit an overkill, and we actually can simplify this. Now I'll show you the way of simplification. Doesn't mean that you should follow for me on this one, and if you truly understand this and prefer a clean and clear understanding of what input goes in which node, this is totally fine. So I will just show you the way to simplify this stuff, but doesn't mean that it become to be more readable, right? It's just a way to simplify the amount of nodes. So what I'm gonna do, I will just click one of those, like this one, x and x1. Let me just show you what we'll do. I will just disconnect that and I'll connect it separately. So you're gonna see we have two different ones, one for x and one for y. But we don't need to do that, because if we have the proper pairs, and even if we don't, it's not a big issue. We're gonna plug x, and then we need to plug the correspondent one to x1. Now the variable is not really properly named at this point. And then I will hold shift and I will do another pair, y and y1, let's call it this way. So as you're gonna see now, let me just delete this. So what we did here is we actually, I used the x and x1 first, and then after that, order matters, y and y1, or y base and y additional 1, into the same formula, x plus x1 plus 1. Now what will happen is it will take these lists one by one. It take one pair, this and this, and then it will take another pair, this and this, and give me literally the same result. And even if I will have one of the elements missing, it still will not change the result. Why? Because, and I said that I will do it every single time when we encounter that, there is a lot of nodes which has data matching in the example of the longest list built in. Now the construct point has the longest list built in, you already know this, and the expression field, as well as other mathematical operations like addition, multiplication, division, so on and so forth, they actually have the data matching built in. So it calculates which list is longest and then shortest, longest and shortest, and take the shortest one and repeat it until it becomes to be as long as the original one, right? So let me bring that back in. So, but as we have perfect pairs, you don't need to do that. So we have the perfect pair 1 and the perfect pair 2, and it processes it one by one. So basically we have the same result, right? Put it into the count. Nothing changes really. Okay, so it's a little bit simpler. And as we already started that, 1 divided by x, I believe I mentioned that, right? So the 1 divided by x is the same as x in the power of minus 1, right? So guess what? We actually have this node already. So if I'll type 1 over x, this is exactly what it is. So I can actually simplify it this way. Well, I'm not saying this is necessarily a simplification, but, you know, there's still have the same amount of nodes, but, you know, just good to know, right, that we have this here on board. And by the way, if you don't know where the node is, let me remind you, Control-Alt, left-click, it will show you in the main palette where everything exists. Right now it exists in the set of polynomials, here 1 over x, or x in the power of minus 1. Okay, all right. Okay, these are out of the way. Let's now go to the concept of rotation. Now let me go back to no additional rows and columns, so 5 by 5 our grid. Now I need to have an option to rotate that. And before we start rotating and figuring out how to rotate this grid of points or directly in values, actually we'll be changing the values, not rotating the points themselves. It will be the result of that later. I need to understand how to find the center of a rotation. And the easiest way doing it right now is we are in the top view and we're using XY plane, our general coordinate system or Cartesian coordinate system. The 0 is right there. So what I need to do is I need to take all these numbers and do something so that all of them will go in to the left, to the negative x and to the negative y, the way that it will become to be centered along the 0 in our Cartesian coordinate space. Well, it's very easy to do, right? So how are we going to do it? We'll bring another expression field and look at the numbers. So we have the numbers between 0 and 1 and 0 and 1. Let me actually do a little bit more interesting thing. Let's increase amount and y like that, right? So now we have from 0 to 1, and from 0 to 1.4, all right? So what I want is I would like to somehow change these values. So some of them will be negative and someone will stay positive, and then that will be somewhere, the center will be somewhere in the middle here and in the middle here. And this is very easy. You will take whatever number you have, like for example, the number 0.2, and you subtract half of the overall length. What is the overall length? 1. Half of it will be 0.5. Here, the overall length is 1.4, right? Half of that will be 0.5 multiplied by 1.4, right? Let me just do it using the formula, right? So I will type x minus 0.5, let's say y. And once again, I would like to notice that these are just a variable. I'll call it elephant 1 and elephant 2, like, because, you know, it's not an x and y, right? It's just my variables, just the default variables. So for the x, I will use these values x directly. So every single one of them. What is y? Once again, this is the maximum length, or the last number, if you will think about that. How we can take for every single list, how we can take the last number automatically, because it's not always 1, right? Here it is 1, here it's not 1. So I need some automation here to find the last element in this list automatically. And we're gonna use a node, very specific node, which use data management, operates with data management on the list level. They locates under the sets in the list tab here, and we'll go from most of them and in the practical sense. So we have this tree, it works on the tree branches and data trees level, and the lists operates with the actual items and elements inside. So the node I need called the list item, this one. Once again, Control Alt left click shows you where it is. So the list item. So what it says, it basically says, give me the list, and I will just plug the data tree with the elements, the list items inside, and give me the index of an item you want to get. And if I will take the index, let's say 5, right? So I will use panel to just input the number, go 5, click away. Click into the index. Now, once again, these numbers are indices, right? But this plural. Index is specific number, right? So number 5, and if I will look at the output, it will give me the value of an element. So it takes me the element 5, which is 1, and the element 5, which is 1. Let's go and says the element 6. The element 6 gives me 0, which is surprising, right? We don't have element 6, and this one gives me the proper element 6 is 1.2. Why the first one gives me 0? You see there is a command called wrap, and it says to true. Now, if I will click here and get set boolean false, it will give me null. So the wrap basically says when you ask for the index which is not in the list, there's not enough elements, it will just start over and start calculating like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth, right? You get it. That's the concept of wrapping. If I'll say the wrap is false, which means we are not wrapping, then it goes to the 6. There are no 6. It gives you null instead. Like, yeah, it's not an error, by the way. It's the null is just actual entity. And here we have the value of 1.2. So somehow we need to give the proper number here, but how are we going to find it? We don't know at every given point which one is there. Now, there are a couple things of doing that. First of all, we're going to use a node called list length, which gives me the length of a branch. So if we'll go into the, let me just kind of use it like this. So list length, so it will get a little bit, or for me, I believe it's LL, yeah. Once again, mine has a quick callout. So it locates under the sets here, the same, here it is, the list length, right? And it's supposed to be somewhere here as well. Let's say, I don't see it, actually, because I'm blind probably, but here it is, list length, right? So if I will plug this series to the list length and check the output, it will give me the amount of elements in the list. So this branch has 6 elements, 0 to 5, and this one has 8, 0 to 7, right? And this is actually my number, right? So we're gonna use 6 and 8 as my indices, all right, directly. But you're going to see that something interesting happened, is that even though that I plugged 6 and 8, it gives me 0 and 0. Why? Because this is an overall length and this is an indice. Remember, it starts from 0. There is 6 elements, but the last one is 5. What we need to do, you already know what to do. Expression, and we will type x minus 1. All right, 1 less. Here we go. Here we go. We have our values. So this is our overall length. All right. But of course, we're going to speed up the process and make it a little bit simpler. And there are two ways of doing that using just only this node. So I will delete this. All right. I'll delete this. And I will not even fill the index. So by default, I believe it's just the index of 0. All right. So what I'm going to do is I will zoom in. And you're going to see that I can get additional outputs. So this is list item 0, this is 1, this is 2, this is 3, right? 0, 1, 2, 3. But I need the last one, and it can be different. What I'm gonna do, I'll zoom in and I click here. -1. -1 will always supposed to give me the last element in the list. And with the wrap option turned on, the -1 will take me to the last element. So this one will be 1 and this one will be 1.4. And here it is, right? This is the first way. Oh, sorry, let me just kind of cut this like this. All right. So this is the proper output. Or alternatively, I can hide this one, give myself the default state. So it takes by default the first element. And I will use the panel and I will type manually -1 and plug that into the index. And I will get the same result. All right. That's it. So I will probably use this option and just plug it here. It's a little bit simpler, I believe. You don't need additional panel for that. And I will plug this value into my y, because this is my overall distance, right? Y. I'll give myself a numbers, and you're going to see it goes from negative to positive, from negative to positive. Then I plug this into my explode tree, and voila, it's centered, all right? Let me just delete this. Organize it a little bit. Now, this stuff is something we will keep, so we will not start over next time. This will be the part of our script, so I will not be deleting it or anything. So I'm just trying to organize it, so it will take small amount of space. Now this one actually not, because we will do some additional modification. All right, so now it's centered. Let me remove additional rows and columns, so we will have only the basic grid. So it's centered. Now we centered it to rotate around the center. They are already in the proper position for rotation. How we do rotation? There are the few ways of doing that, but underneath that all, there is a concept of 2D transformation matrix, or the specific one of those which called a 2D rotation. Of course, this is the description of the transformation matrix, and it is a formula. So what I will do is I will bring the formulas and I will do the rotation, and then I will explain how it works, okay? So I will use my explode tree here as well. I want it to be here. But instead of creating points right away, I actually delete this, right? And I will operate only with the numbers. So this is my x, this is my y. Now, because I don't have a point, there is no data matching right now. So I need to data match both of those, and I will use the longest list instead. Once again, I'm using it separately because I don't want to construct points. Sorry, because I don't want to construct points yet. I will rotate and then construct points, but I need the proper pairs of data, right? That's why I'm using the longest list, which was baked into the, well, you already know, I mentioned it multiple times. So here, as graphed, we have ourselves the bunch of data for x and y. And by the way, I can always change the name. So if we right click, type X, enter, right click, type Y. If you will not click, type enter and click away, it will not change the output. The output will be list B, right? Okay. So it'll be a little bit shorter. So x and y, and then I will actually start using formulas for rotation. So expression. Now it looks like follows. And by the way, guys, you actually most likely learned it in school. You just completely forgot it. And of course, the description of this formula was vague in school program for reasons. So let me actually bring it back here. So x multiplied by cosinus alpha minus y multiplied by sinus. Now it's not an alpha, it's a. I'll plug. It's just a variable of an angle, right? Okay, hit OK. Now I'll click here and I will bring this variable here as my angle. Now I will Ctrl+C, Ctrl+V, duplicate. So this will be component for x, the new x, and this will be the new y. So this one will be x multiplied by sinus alpha plus y multiplied by cosinus alpha. All right. Now I need to bring the degree, or basically the angle, and I will do it using the very familiar degrees. So I will type, let's say 90. And I will, it goes from 0 to 100. Let's go right click and we will go to edit. And in our number slider, I will change the maximum value. Just click and drag, or, oops. Oh my God, let's do it again. Let's type this. Don't drag, guys, don't drag. Yeah, let's go to 90, like this. All right, 0 to 90. Okay, I will actually, I will probably call it right now angle, and then I will convert it to radians. So once again, I will just explain everything in the detail, don't worry. So radians, and I will plug that into the A, because this is our angle. So x will go for x, y will go for y. All right. Let's organize a little bit. I don't know, something like this. And then let's construct the point. Now, as we already, once again, I'm using the quick collab. So x goes to x, y goes to y. And as you can see, I'm not grafting anything because I already have the proper pairs, right? And now we have ourselves the same grid with already rotated 90 degrees. Well, you don't see this because it's, it's isotropic, but here you're going to see how it's actually doing this. Yeah, fantastic, right? So this is exactly what I want. Now it is time to dive into these ones and understand what these formulas actually do and how it works. And of course, because it has sinus and cosinus, we can't understand how this formulas works without first remind ourselves what sinus and cosinus actually are. Now, it really depends on, once again, where you studied and what you was told back in the day. But if we go just to the bare minimum, to the school program, then sinus and cosinus described through the geometry, pure geometry. So there is a triangle fit into the circle, and the relationship between the sides of a triangle give you the sinus and cosinus, right? Now that's okay, and this is actually how humanity first designed the concept or found this relationship and call it sinus and cosinus. That was like 1500 years ago, but much later, like 1,000 years after, we found a better explanation of what the sinus and cosinus are. And that explanation never given you at school, because to fully understand that, you need to know differentials. However, I still believe that when it described through the geometry, it's just too vague. It's too vague to remember and understand, and it's become to be more like a like that as sinus and cosinus can't live without triangle fit into the circle, but they can, because they're not about the triangles and they're not about the circle. They're a completely different thing. Well, of course, you will learn it if you go to the college and you're like, do you want to be a an engineer or PhD in mathematics, then of course you will be given all the details. So what I will do is I will explain it the proper way, like a little bit more complex than it explains in school, but I will avoid diving very deep into the heavy duty math when it comes to the differentials and integrals and limits and so on and so forth. So we will not be calculating them, but I will show you where it originates from. So you will understand it on the logical level, so the pure logic, okay? And then through that, we will understand how this formulas works. So let me bring a formula for you. Now the formula looks like this. Okay, this is a formula of perfect motion. And if you're familiar with differentials, you know that this is a differential because this is a second derivative of this. Now, the second derivative is acceleration. The original formula, the original function is a position. So this formula describes perfect motion. By perfect, I mean that there are no losses any way and form, because it can't work in real life, because in real life we have friction, conservation of energy, you know, there is a lot of forces affecting the motion of, well, whatever we have, right? But in mathematics, we can design a system or describe the system in time, through time. It is a differential once again, and t is time. That actually can describe the behavior of a system and like a snapshot in time at every given moment for idealistic motion, which doesn't have friction, doesn't have motion. It's endless. The more time goes, the more it replicates itself over and over and over again. So this formula has, because it's a differential, it has a default values or base states. Let me describe them. So the first one, the function itself, this is position. The second derivative is speed. And the third one is acceleration. Once again, I'm not diving into differentials really deep, just on the logical level, okay? So, these values are related to each other, and with the specific parameter of speed and position, the formula will work. The formula basically says that the acceleration at every given time equal to negative position. And this formula has specifically two sets of base values for position and speed, which combined give you infinite amount of possibilities or the solutions of this formula, which is true to this state where acceleration is equal to the negative position. So the first set of these values will be position. The position will be 1, speed will be 0, and acceleration will be negative position. I will just let it as is because I believe it's quite obvious. It will be minus a function of time. So the second one will be shifted on quarter of a period. And I will explain it in the graph really, really soon. The position will be 0 and the speed will be 1. And with the same base state of a system, it still will be true that the acceleration will be equal to negative positions. So both of those give you the same result, and the combination of them give the same result, but in different possibilities in terms of the position and amplitude. So now it's probably mumbo jumbo, right? So let me just visualize it. Imagine that I have two axes, just a graph to visualize what's going on, right? Now, please note, this is not a Cartesian coordinate system. It's just two axes. One of the axes is time, and then the other axis is position, okay? So the first states will be 1 and 0. So, which means that the position is 1, let's say here, right? And the speed is 0. So it's basically right there. Another value will be position 0 and the speed of 1. Now the time goes to the right. It doesn't matter in which, like it's linear, right? Is it like 0 and then 1 and 2 and 3 and 4 seconds or milliseconds or, I don't know, elephants, or it doesn't matter. It is just the number which increases. You can think about that as a flow of time. And in fact, you're supposed to think about that as a flow of time. It's originally designed, but it's actually just a number that increases. We will think about that as time for now. So what will happen is that at the position 1, right? Let's say this batch of numbers. With position 1, speed is 0 and acceleration is equal to negative position, meaning that acceleration pushes this point to its opposite state right here with maximum force, maximum acceleration here. Speed is 0. So when we increase the time goes to the right. What will happen is it start increasing the speed, right? Goes through the 0, and then at every given point, acceleration equal to negative position. It actually now goes to the opposite direction. It starts to slowing it down. Speed goes to 0 again. It pushes all the way to the other side, and then it just going to go increase again, and then goes to the 1 again. And guess what will happen? It will move and move and move and move. Now follow this motion described by 4 numbers, 1, 0, -1, 0, 1, called a period. But we will talk about that a little bit later. Okay. So this is the plot of a position in time using this formula. Alternatively, this one, it starts from 0, but it actually has the same, the same behavior. It has a maximum speed. It has, and it just basically goes the same way. It just does the same thing, but it shifts in a quarter of a period. It's the same function, right? It just goes in. So it does the same. It goes to the 1, it decelerates, then just start to pushing it in the opposite position. It accelerates again, and then just so on and so forth. But it just the starting position is in a different place. This one at 1, this one at 0. Together, then combined, they can do every combination of amplitude and a length. Okay, so and we decided that actually the solutions of the formula with these default states were position 1 and speed is 0 called cosinus, and 0 and 1 called sinus. Once again, solutions of a differential, we solve it through the polynomials. In academic, in the books, it's actually described through the Taylor series. In the actual systems, the FrameNet on your computers and calculators, we actually use Chebyshev polynomials to solve that. Well, don't worry about that. It gives you a number. The result is always a number. So one of them is this batch of numbers, basically, when we plug this one in the state and move the time, is a cosinus, and these ones will be sinus. All right. Okay, now let's describe the system a little bit differently. I will draw another graph. This time, I will use the same two axes, so the vertical and horizontal. Once again, it's not a Cartesian coordinate system. Not a Cartesian coordinate, it's just two axes perpendicular to each other, 90-degree angle. But instead of using this horizontal as a time, I will put a time out of the graph. Now, remember, we have numbers. How we visualize these numbers, well, it's up to us. We can do whatever we want. So I'll put the time away. Instead, I will use these axes for representing the cosinus, or results for these values, the position, right? I call it position. You're gonna get no, I don't want to put it into the, yeah, it will be confusing. So let's say that this is our position or for cosinus 1, and this will be our sinus. In other words, how I can explain it? You know, let's fuck it. Let's talk this way. So once again, two graphs. I'm sorry, guys. So two coordinate systems, and I will plot the position separately, because right now position is on the one vertical axis, 0 and 1 on the vertical, on the vertical axis. I will spread them. One will be here and one will be there. So this is 1 and -1, and that basically will be my cosinus, right? The position for the cosinus goes like this. So this is P. This is P also, but this one will be for the sinus. It goes from 0 to 1 to -1. So when the time, if I will increase the time, what will happen is that the cosinus will goes to the right, from the right to left, then to right, then to left, then to right. Imagine that I'm changing time somewhere outside of the system and driving these values. And this one goes up, down, basically forming a cross, right? Cross with a shift of a quarter of the period. When one of them will decrease, another one will indeed increase. So now let me visualize both of them, and you will understand what it means on the actual example. So hide this. Control Q once again. So first of all, let's look at this graph, but in more accurate environment. We're looking at this in the Grasshopper. Don't worry how I made it, it's not important. So turn that on. So from our first graph here, you see that this red line represents the values of a cosinus. So this is a cosinus. The x, you can think about this x coordinate is our time, and the y is our position, right? So this is cosinus. This is sinus, right? Same thing. Two waves in a way. This, once again, not x, this is time. This is position. One goes to 1, then go to 0, to -1, and so on and so forth. And these numbers, this plot calculates based on these, solving this differential. All right. So together, they give me, as I said here, I didn't really draw it, but together, sinus and cosinus will give me all the possible solutions which will be true to this formula. All right. So basically it gives me how many sinuses and how many cosinuses I will take as a factor. You see, f1, f2, a factor. So now it is one sinus and one cosinus. It gives me this wave, right? But I can, for example, take only sinus or only cosinus. Here we go. Or I can mix and match, for example, like this or like this. It's up to me. All of them, there is infinite amount. All of them will be true to the formula and always be give me the proper result. Just combine. Okay. Now it's important for next parts. Okay. So here is another example with the different description of the same data, but I removed the time, right? So here is this example of that. Let me turn that on. I'm doing it using middle click. Middle click, there is turned off, turned on. Sorry, I probably didn't really mention that, right? Let me hide this. Right, so let me go into the time of 0. Now, as you're gonna see that there is no time, I'm changing the time here using the slider. So at this time 0, we have the component of cosinus with the position of 1 and the sinus at 0, right? And I will start moving this time, I'm driving time. You're going to see that exactly what I showed you in this graph. We just put the time away and separate them on a separate axis. When cosinus decreases, sinus increases. When cosinus increases, just with the negative value, a sinus decreases. So as you're going to see, they're kind of drawing me or moving into this kind of like a cross, right? And they always shifted and compensating each other because they have a shift. We have a shift here, but the quarter of a period. When the axes are perpendicular, it will be 90 degrees. So we shifted by the by 90 degrees, right? One increase, one decrease, one increase, one decrease. Okay. Now, this is the nature of these numbers. How we represent the numbers, as I said, it's up to us. We can take any coordinate system, any way to visualize the data. And we visualize it with a perpendicular axis. We're basically enhancing this idea of a shift, the natural shift of the starting positions for the formula. And this is the actual and a natural shift. We just visualize it this way, which is really convenient. But let's move further, because right now it's not a Cartesian coordinate system, right? And we need Cartesian coordinate systems. Our computers works on Cartesian coordinate system. We need to visualize points. We need to visualize geometry, and for that we use Cartesian coordinate system. And it's very similar, right? To axis or free axis, we have z, of course, but right now we are looking at the planar example of that, like x, y, and they are perpendicular. But there is a difference, because before that you're going to see that I'm moving time, which is not on the graph, and I have these two values. This is a pure number and this is a pure number. For example, the cosinus at this point in time is 0.76. This one is 0.63 at 0.693 time. Now, once again, we get these numbers by solving a differential using, in the terms of the Grasshopper, using Chebyshev polynomials or stabilized polynomials. I will not dive into that. It's not important. Well, I mean, it is actually very important, but it's not important for us because the computer does the math for us. And to understand it, you need to go to the polynomials and understand differentials and understand integrals, which is a couple of years of heavy mathematics. So put it aside. We have these numbers, and if we remind ourselves what Cartesian coordinate system is, and can we actually take this concept with the two separate axes and their values and basically represent it as a Cartesian coordinate system, we need to do very little actually, because it's already in place, right? We have a component, we have the one number or the one value, we have another value. Now in Cartesian coordinate system, every value represented not by a single value but two values, because in Cartesian coordinate system we operate with vectors. So if you imagine right now that this value which we get through our perfect formula, the formula of a perfect motion, if we want to represent it in Cartesian coordinate system truly, because instead of these two values we need to find the resulting one, right? We need to represent this number as two numbers, as a vector. What is the vector for this number? For the number 0.769 in Cartesian coordinate system, if we assume that this is the x direction? Well, 0.769, or let me just kind of draw it. 0. Oh, sorry, what I'm talking about? We are talking about the cosinus. The cosinus here will be, my bad. The cosinus here will be 0.769 0. And the sinus will be 0.638. So basically this is a vector. The first one, the x, is a vector in Cartesian coordinate space, and vectors describes, it doesn't describe a position, it describes in what direction and how far, right? So basically this 0.769 become to be the amplitude of the vector, and basically says x 0.6769, y 0. For the y component here, this one, it will be 0 for x and 0.638 for y, right? And to find the resulting vector, and vector and the point in Cartesian coordinate space are interchangeable. Now, they're actually the part of the same thing, described the same way. What we need to do is we need to add them up component by component, right? So in return, we will get ourselves a 0.769, 0.638, because there are zeros, right? So this is actually a vector which goes between the two, somewhere here, right? It basically says 0.769 to the right, 0.638 to the top, right, on x and y component. And indeed, this is exactly what it is. This is the vector. This is a vector, all right? So, this vector, as I said, in Cartesian coordinate space, it's a vector and a point, because the point described by the same three numbers. I'm saying three because we have z, it's 0, 0.6769, 0.638, 0, right? Because the z is 0. The same for the vector, meaning that we actually are going to describe it as a point. Yes, it is. This is indeed a point. Now we're gonna truly say that we used our concept of perfect motion, its solution, its starting positions for solution of this formula as a cosinus and a sinus, right? And we visualized it in our Cartesian coordinate system, all right? Now there is still this slider called time, all right? And when I increase the time, you remember that in this graph we increase the time and it just endlessly goes and goes and goes and goes. But because they are now perpendicular, these values are perpendicular to each other on a perpendicular axis, you're going to see that when one increases, another one decreases. And in Cartesian coordinate system, we basically construct a resulting vector of the two. Basically, the sum, doing a sum operation between them. And when we increase the time, instead of moving to the right, it basically moves in. It goes right, up and down, left and right, up and down, left and right. But if you look at the arrow, instead of a cross, there still moves like a cross, right? But the actual resulting point has a circular motion. And if the time will be longer, it will be just rotating and rotating and rotating and rotating and rotating endlessly, and the values will go and change between 0 and 1, 0 and 1, 0 and 1, and these 1, 0 and 1, 0 and 1, 0 and 1 all the time, and this one goes, and with time increases, and it's not going from 0 to 1, it's constantly increasing, right? Well, it will be rotating over and over and over again. And that's why the Cartesian coordinate system represents these values. Like it's logical that it represents it this way, right? Because we spread them on the different axes which are perpendicular to each other, enhancing the fact that these two has a shift in the period, because one of them starts at 1 and another one starts at 0, right? So does this motion circular? Yes, and this motion is circular. And the motion is circular because this length of a vector never changes. And in fact, this length is always 1. Why? Because we didn't really use any additional factors like in this example, right? I didn't even use any additional factors. I took the pure sinus and a pure cosinus. And if you remember the Pythagorean theorem, you probably remember that it says that in Cartesian coordinate system, x squared plus y squared will be equal radius squared. Radius, like this, squared, okay? Meaning that the radius will be square root of x squared plus y squared, right? A beautiful Pythagorean theorem. What is x and y? For us, sinus and cosinus. We use the values of sinus and cosinus. This are my x, this is my x, this is my y. It has zeros. That's why in school program they just chop that off and like one value, like x value, y value, not two values but one. But once again, we are not in school, and this is of course a vector, so two numbers. So this x and y are actually sinus and cosinus. And guess what? The sinus squared plus cosinus squared will be equal 1 squared, just based on the formula itself. Meaning that, what is 1 squared? Just square root of 1 will be equal 1. This is a vector with a radius of 1, and it never changes. So here it is, the length of this vector. You're going to see that the length of this vector, this one, is 1. And if I'll move the time, it will not change. It's always 1. Okay. Now you're going to see that sometimes we have 1, sometimes 1.0. Now that just goes to the precision which we calculate our sinus and cosinus. Once again, we are working with the Chebyshev polynomials. They are very accurate and very stabilized, but it really depends on the amount of floating points, because we always calculate sinus and cosinus to some precision. We can't be infinitely accurate with that, as with the pi, right? The pi number, once again, we calculate it as a polynomial as well. We can't describe it with a single formula. We can calculate it with a specific tolerance. And because the tolerance is a little bit wobbly, right? We're going to have like the 1 or 1.0. But that's probably the story for another day. So it is indeed 1. So this is indeed a circle. No matter at what time we have, the length is the same. And because the length is the same, the circle, the point sits on a circumference. Okay. All right, we're getting closer and closer to the solving the formula, right? And while we're doing that, we, on top of that, remind ourselves or learning or what is sinus and cosinus actually are. All right, well, actually, why I closed that? Let me put it back. Okay. Now, when we understand what the sinus and cosinus and how they represent this circular motion in Cartesian coordinate system, because now we're going to say that we are in Cartesian coordinate system, we need to look at this slider, which is called time, right? Time. So why I'm still calling it a time? Because it was originally time. This is indeed time. It wraps around and around and around on this graph, right? So calling it time is, well, correct. You can call it time because its roots comes from the fact that this is a time. But do we have a better explanation of this number in our Cartesian coordinate space, knowing that this point moves in a circle? So basically, it basically draws a circumference for us with time, you know, that is basically some kind of an arrow, some kind of an angle in Cartesian coordinate space, right? It's just not in degrees. It's just a number which grows and grows and grows endlessly and wraps and wraps and wraps around. Can we describe it somehow like something different? And of course we can. For that, let's quickly get to complete basics, right? Just pretty briefly. Now, imagine that this is a circle, all right? Yeah, it's difficult to imagine. Oh my god. Okay, it's really difficult to draw with a mouse, and I don't want to pick my Cintiq because it covers my everything. So now imagine that this is a circle, right? And this is its diameter. Now you probably know from school that circle in geometry described by 2 pi r, right? Probably heard this formula multiple times. You can even ask if you ask anyone, they say, well, circle, mathematics, 2 pi r, right? 2 pi r this, 2 pi r that, great. But if you ask them what is r, some people say, well, r is a radius, right? The radius. And some people say, no, it is a radiant, which is a different thing. Who's right? And how this stuff, relates to our time slider. Well, first of all, both of these people are right because we have two formulas. They are very similar, 2 pi r, but in one case r is a radius and in another one r is a radiant. To understand that, let's get through the radius first, right? So now our ancestors a long time ago figured out that there is a specific relationship between the circumference of a circle and its diameter. Very specific one. So the length of the circumference, so the circumference length will be equal to 3.1415 and so on and so forth of its diameters. All right. But the formula stays 2 pi r. Why 2 pi? Because if we switch the diameter to the radius, it will be this distance, right? So twice, smaller. And because it is twice smaller, we need twice the amount. So that's why the formula goes to 2 times 3.415 of its radiuses, or 2 pi r as a radius, right? Now this formula give you a number, so it will be a number. And this number is the length of a circumference, the actual length of a circumference, right? So it describes the circle, but it describes the circle for the length of the circumference. Is it useful? Oh yes, of course it is. It is very useful, used all the time. But there is another one, and it describes the circle not through the circumference or the length of a circumference, but through the maximum angle, and it based on radians. So instead of a radius, we have a radiant. What is radiant? Radiant is an angle formed by a radius fit onto the circumference and a radius which forms an angle, right? So these sections, radius fit on the circumference, angle between the radiuses, right? This number called a radiant, all right? How many radians we need to describe the circle? Well, as many as radiuses, right? It's the same stuff, it's just a radius fit on the circumference. So the same, 2 pi, let's call it different, let's call it this way, 2 pi radians. It gives me the number. Now these values, 2 pi r and 2 pi r as radius and 2 pi r as radians, are perfectly identical. They give me the same number. But this number describes the circumference, and this number will describe an angle. It's true because it's true when the radius is set to 1, because when radius is set to 1, the actual radius is equal to the radiant. They basically the same number. If the radius is bigger, then not, but the radiant is still the same, because we still need 3.2 times of 3.14 or 6.28 radians to describe a full circle. It's called the full circle, right? It's basically the measurement of an angle, right? Now remember, what is 2 times pi? Like 6.28 and a little bit more. Let me look at the time again. What's I set at the maximum? 6.28. Why? Look at that. So it's really related actually to actual formula, 2 pi r, and it's true to the radius, it's true to the radiant. But as it is become to be here, just visually, it's really easy to understand that this actually can describe the angle, because you can see the inclination of this vector changes, right? Inclination changes. It's actually so useful to describe the angle using this number. The number is always increases, right? Yes, but we still can describe it as a measurement of an angle. What is the full angle for this will be? Well, let's calculate. Let's look at the formula. It will be 2 pi radians, or 2 pi radiuses, if you will. It's 6.28 and a little bit more. It's not like almost, right? Like 2 pi. Okay, so what is this number is? Well, if we represent it through the actual description of a circle, it is a radiant. So this number is a radiant. What is the slider itself? The actual set of these numbers, the domain of these numbers, what is it? It is a period. 6.28 will give me the full circle, or the full motion of our value between the values. So 1, 0, minus 1, 0, 1, full motion, and for the cosinus and for the sinus. And it does this when we get through the time of 6.28, right? Like this will be full, and then it repeats itself again and again and again and again. So this 0.28 is actually a full period, and the slider itself we can call period. So this is a period, and it measures in radians, and radians are the number which is constantly increases, right? It can be really, really big. It means that we just wrapped it around multiple times, right? So is it still time? Yes, in pure algebra and description of this formula, it's still time. But when we are describing it in Cartesian coordinate system and we already have a description of the circle, it's actually really useful to call it a period and call this value as a radiant. And as we need to measure the angles, that's the best way of doing that, using the radians, because it's the actual number which is described, right? And of course, there is a different ways of describing the angle. The most common one in day-to-day life is degrees, right? So we're not using these number of time or radians as describing our angle, right? We're saying 30-degree angle, 40-degree angle, 90-degree angle, but it's a made-up stuff. We decided that the full circle, 6.28, the full period will be 360 degrees. which means that the half of it will be 180 and a quarter of that will be 90. Extremely convenient for us to calculate and measure and quickly understand, because when I will tell you that, oh, let's go to the angle like, I don't know, 0.494. Well, what? Where? And it's actually much easier to say it in angles, right? Just roughly. So that's why we use angles. And there are another set of people, a lot of scientists, by the way, which push it in the different direction and say instead radians and sorry, my microphone, my bad. So instead of angles and radians, they are thinking about calling it a tau. The Taoists, the people call themselves a Taoists. You can actually Google them. It's quite an interesting story, and they have a lot of logic behind their idea. But a long story short, we of course can calculate and convert degrees to radians and radians to degrees, right? It's very easy. So, we have the radians over 2 pi, right? So 2 pi divided by 360, or depends on what we want to convert to what, or 360 divided by 2 pi, right? So very simple. And this conversion just gives us an ability to convert one to another, degrees to radians, radians to degrees. Okay, that's I believe that's it about the sinus and cosinus as a pure concept, and the radians as well. And now we can go in and actually look at the formula. So let me hide this thing like this and turn on this thing. Now, guys, it's not important, once again, how I did that and what kind of an also. Sorry for this spaghetti code. I was bored because I'm a lazy asshole. I was bored to do it beautifully, but because it's not important how it made, where we'll be looking at what it actually represents, please don't worry about that, right? So here we have this formula. Remember, for x and for y, 2D rotations formulas. These one and these one. One for x, one for y. Here they have it. One for x and one for y. I will be describing how they work. As we already know what the cosinus and sinus are, now we can understand how the 2D rotation works. So imagine that we have, let's say, a point in cyan. So let's look at the cyan lines first. Now imagine we have this point, right? It's with a specific position, at the specific position. We calculate that, we know this. Like in our grid, for example, right? If you remember, we have, I won't be turning it on, but you understand we have a lot of points, right? Every point already has a position. We know the values of x component and y component. We already know this. Now imagine that this is one of these points. And we know that at x component, described for the cosinus, is 0.69. Another one is 0.72. Once again, we always can calculate the actual values. So this is the sinus of 46, and this is the cosinus of 46. 46 of what? 46 degrees. So you may imagine that this point is already sits at the base angle of 46 degrees, somewhere here, right? So rotate it from 0, whoop, like this. And it has a specific set of numbers, 0.72 and 0.69. This is the sinus of 44 and cosinus of 44. Now what we need to do is we need to rotate these points on 10 degrees. So basically add 10 degrees. Now right now I don't know where it's supposed to be, but what the actual numbers, what the actual components for its x and y projections, I don't know, right? I have no idea. But what I know is that it's, now of course I know, like I did it, so I know where it is. So it's supposed to be right there. How I tell the machine add plus 10 degrees. How are we going to do it? Well, I do it using very specific formula, the ones you're going to see here. Let's look at the first one, because there are two of them, one for the x component, for the new x, and another one, this one, is for the new y. So let's look at the first one, this one first, at the x. Now it says x multiplied by cosinus of an angle. And this is the angle A is our additional 10 degrees. We want to rotate on 10 degrees, right? So x multiplied by cosinus A minus y multiplied by sinus A. And this A is these additional 10 degrees. So first things first, we will calculate what is 10 degrees, right? What is 10 degrees in our Cartesian coordinate system? Well, we will use the sinus of 10 degrees and cosinus of 10 degrees, right? we convert it to radians. I already show you how to do it. It's very simple. So I'll convert it to radians, and I will calculate the cosinus of 10 degrees in radians, the sinus of 10 degrees at radians. Remember, these radians are our time, these one. I have to plug these values, right? I'll get myself the actual state of a system at the given point, all right, using the differential. Of course, computer does it for me. It gives me the numbers. It gives me the number 0.98 for the this green lines and the green points. So it gives me this point here. Because it will have the cosinus will be 0.98 and sinus will be 0.17. Once again, differentials solved, it gives me the numbers. So I know that the original values for the 10 degrees are these. So now I have x, which is my original projection of my original point on x direction. Here it is, x, it is 0.72. And I have the cosinus of an angle of 10 degrees, right? Which is 0.98. Let's solve left part. X multiplied by cosinus A. What will happen here? Basically, it says take the current position of a given point, which is 0.72. So let's take 0.72 and take it 0.98 times. What will happen? Well, I believe it's obvious we're multiplying on the number which is smaller than 1, meaning this number will become smaller. Where it's supposed to be to get the actual 10 degrees, it's supposed to be right here. What will happen if I will multiply? We will go there. Just by looking at these numbers, nah, not even close. It goes a little bit, but not where it's supposed to be. Let's actually show you. This is where that point will go. So if I will take 0.72, 0.98 times, once again, x multiplied by cosinus alpha, it will be right there. But remember, these cosinus and sinus works in tandem. One increases, another one decrease, one increase, another decrease, one decrease, another increase, right? Because they are in the quarter of a period shift. So I need to really find the proper x point. I need not only find the ratio between the current point projection and the additional 10 degrees, but actually calculate the same for y and subtract one from another. Otherwise, the vector length will be different. And I will move the point, but not on the 10 degrees with the same the amplitude, but it will be bigger or smaller and stop being on the same coincident to the same circle. So when I increase something, I need to compensate it on the other projection. So basically, once again, they all work in tandem. One increase, another decrease. So let's do for the x component and compensate it with the y. It says y multiplied by sinus of an angle. So we already know this. Sinus of an angle A, once again, it is 10 degrees, it's 0.17. The original y of this point was 0.69, meaning that we need to do the following. We will take 0.69, and we will take it 0.17 times, right? You already guess where the point will be. It will be pretty small, somewhere here, right? We'll just really take it. We didn't take it much times, right? So in overall, you're going to think of this formula as x multiplied by x1 minus y multiplied by y1, where x1 and y1 is a projections of a new angle at which we want to rotate. Why it has this description instead of this description? Well, because this is a matrix. It's just the 2D transformation matrix. I will not deep diving on that right now. Maybe in the future scripts I will show you how it actually works, where it originates from, and why it represented and wrote the way it is instead of this one, but it's a story for another day. So now we have these two points. So we have this point, which is this left solution here, and we have this one, and we have this point, which is the compensation for the y. What are you gonna do? Subtract one from another. Subtract this and this and this. Let's do this. So if we will subtract from this, we will get exactly the proper position. You see, I subtracted this one from this one, and I subtract this one from this one. So the proper term, and here it is. Bam, This is our proper point. It's actually, I know that this is exactly where it's supposed to go. This is the proper projection of this point, right? So we calculated the x, the new component of x, or the new vector of x. So it will be number and then 0. So whoop, in this, go to the x direction, go to the right this amount. We know this value. Here it is. But this is on x. Now we need to calculate the y as well. For y, we have this formula. Let's go for this formula as well. So first of all, x, the current x, which is 0.72, will multiply by the sinus this time, but this one 0.17. Guess what will happen? We'll get the very small amount. Remember the previous one? This second section was small. Here the first section is small. That's not a coincidence, right? So this is a very small value. Let's go another one. And once again, we are talking about these values, these components, right? So now let's go to the second part, y multiplied by cosinus. So the y is the y component, which is 0.69, and we'll multiply it, we'll take it 0.72 times, which will be this value, right? Very familiar, isn't it? Just invert it. So now what we're gonna do, we will add them up. So remember, this is y right now, not x, y. So what we need to do, we need to take this and add this one. And this is exactly what we do. Bam, we have our point. So now they have this one, this point, and this point. And I have 2 points in Cartesian coordinate space, which every single one of them, once again, described by, in 2D, 2 numbers, and 3D, 3 numbers, right? It's a vector. We just sum them up, and we get ourselves a point. Bam, bam, here it is. So the formula, these two formulas, they are not calculated, they're actually not calculating angles. It operates based on the projections. So I want to have a rotation on additional 2 degrees. I'll calculate the projections over 2 degrees in this Cartesian coordinate system, and then add or subtract from the current point projections, and that's how I'll get the new values. So basically the formula doesn't know the current angle, it doesn't even know where the point's supposed to be, right? You calculate projections, you operate within projections, and this is a standard operation in Cartesian coordinate system. That's the beauty of it, right? So that's how it works. Now before we end this, let me take the now I can change the angle if I want, but let's say that it will be still 10. I'll just move it on this side, right? Just to prove my point that this formula will work all the time for all the angles, and that this minus and plus is always the case and always true. So now let's quickly look at the same situation, but now we have point here and we need additional 10 degrees. What will happen? X multiplied by cosinus alpha. X is negative now, right? The original one is 0.98. It basically says take 0.54, negative 0.54, 0.98 times. You already know where it will be, a little bit shorter, right? So it goes. So it's got to be smaller. Now let's go to the y. The same thing. Y is a 0.84. We will take 0.17 times, and the same result, it will be small. Right now you see we're subtracting. Now here we subtracted, one was big, another one small. Here we subtract, well, what's going on? So it's becoming even smaller. That will be wrong, but it will become bigger. Why? Because this value is negative. Negative 0.54 minus whatever value we have here, minus this. Minus plus minus give you plus. It will increase. So no, it won't give you plus. Minus and minus will be even bigger negative value. What is the bigger negative value? Goes into the left direction. So the actual result will be even bigger. Here it is. Bigger negative, right? Is that true? Yes. Let's look at this one. X multiplied by sinus alpha plus y multiplied by cosinus alpha. So absolutely same thing. So the current x is minus 0.54 multiplied by the sinus of an angle of 10 degrees. So we take is minus 0.54, 0.17 times. It's small, right? Obviously, the y multiplied by cosinus 0.98 will be pretty big, like this. What we're gonna do? Once again, we're talking about the y right now. We sum them up, right? And because this one is negative, remember that x is negative. When we sum them up, it will be current position plus, minus, negative, it will make it smaller. All right, bam, here it is. Let me just kind of hide this. This is our yellow point. Here it is. Is it correct? Yes. This one correct? Yes. We have two coordinates, no x, no y. And that's true for absolutely any angle, of course. It always calculates me the proper positions, right? So I believe this is convenient now. Now, I don't know if there is a better way of explaining this, but I believe it's just very visual. And I hope now you understand how this formula works. So this is a 2D rotation formula. This is the part of the bigger transformation, 2D transformation matrix. And it's actually designed to rotate in objects in Cartesian coordinate space, or orient, probably better say. All right. Okay, so that's how this formula works. So let me now turn that off and turn our grid on. So this is our grid. All right. So I actually set the angle to 0. I will get 5 by 5, 0 by 0. I will delete the original grid. Behind the scenes, I will delete all of this kind of, all its text and stuff, all the unnecessary features. And in the next lesson, we will proceed where we left it, because now we need to push it back from 0 to positive y, x, from 0 to positive y, because this position was for proper orientation. And we will proceed with further and add a little bit more additional, add additional features to this grid, and then go to the actual construction of a hexagons. So thank you very much for watching, guys, and I will see you in the next one.